Okay, so it's a great pleasure for me to have Cesare Miglioli in the LDS seminar series. So Cesare is currently a postdoc at University of Pittsburgh. Previously, he was a postdoc at Purdue University. He has training in different areas of statistics, and he did a PhD at University of Genova. He spent some time at Max Planck, and he has a bachelor in economics from Bocconi University. He has a lot of interesting project and works on graphical models, computational statistics, and many other topics. And today it's great to hear from him about more or less a Rashomon algorithm for sparse model sets. So thank you, Cesare, for your kind availability to present in our seminar series.
Thank you, Alessandro, for the invitation, and I'm happy to join the LDS seminar series. So as Alessandro told you, I have somehow at the moment many different interests, and this is one of them, which I think could be also of interest potentially for the audience, because I will tell you in advance there will not be a lot of math in this talk, but I think there will be a lot of ideas, especially interesting nowadays, where the AI is kind of course, the dominating paradigm and interest of many people. While we're going into a bit a different type of direction, but still, I think very interesting. I hope I can convince you about this. So the work I'm going to present to you today is a joint work with Roberto Molinari, who is a professor at Auburn, Gaetan Baccali at Lyon, AM Lyon in France, and Samuel Orso and Stéphane Guerrier at the University of Geneva in Switzerland. So the title, more or less a rational algorithm to sparse model set. At first, I need at least to introduce a bit of notation. It will be probably one of the most technical slides. There is not much more than that. But you know, one of the main paradigms in machine learning is supervised learning. The other is unsupervised. What is the difference between the two is that, of course, in supervised learning, you have a Y, so you have a variable of interest, and usually you have some data set with an X, usually a matrix of observation, so let's say N observation and P predictor. And we want, when we have supervised learning, taking as input the X's, say something about the Y, for example, prediction. But in science, we are not only interested in prediction, which is one of the main topics, of course, of machine learning or AI or whatever name you want to give this type of disciplines. But actually, we are more interested also in the explanation. So we would like to say something about Y as a phenomenon. Let's be more concrete. So imagine that Y is related to the presence of or an absence of an illness. Like we will talk today, for example, about breast cancer. So let's say about a cancer. We want not only to be able to predict very well if a person given some attributes, some characteristics that we can observe will have cancer in the future or not. But also we are also interested in what are the drivers of the cancer, because also this will help us to design new treatments, to understand better the phenomenon. So there is always this balance. So we want, of course, to be very good in prediction, but we want also to be very good in understanding the phenomenon. And this is actually the topic of model selection, which is, I would say, a discipline which is more at the base of statistics. So, of course, when you want to use this X matrix to learn something about the Y, usually you have a model class in mind. Model class is a very generic term. You could think about this as the most vanilla type of like linear regression, logistic regression, well known to doctors, but more advanced stuff like random forest or support vector machine or any type, a neural network, whatever you can think of here is this model class. But when you want to do model selection, actually, this is a bit of something that needs to be underlined. You don't really want to talk about the model class. Let's say that you have selected the model class, let's say the class of linear regression, which is probably known to everybody. Now I want to understand which are the values of the X matrix, so somehow the variables that are the P predictors, which one among them are important to describe the phenomenon. So not only talk about prediction, but also to describe the phenomenon. If I hope many of you have had at least one class in statistics, and about these topics, usually this is the classical figure that you see. This is coming from the Elements of Statistical Learning, one of the most well-known book, I would say, in statistics as well, where you see basically what is the trade-off between selecting a given number of variables in a model. So on one side, you have, imagine that you just select one variable to predict a phenomenon. Of course, this variable, just have one variable, so your estimators now will have low variance, but high bias, because of course, maybe your phenomenon is explained by more than one variable. And as you go on following the model complexity, so you increase the number of variables, then you will reach a situation in which you have more variables in your model, so maybe the bias will be lower, but the bias will be higher. Actually, if I present now this picture to a machine learner or to an AI expert, what it will tell me, that I'm stopping somehow I'm just showing the figure a local part of the plot. And it's true that when the model complexity is very, very high, so imagine that this graph and this picture, this plot continues on the right, up to billions and more than billions of parameter, then you will see that probably this red function goes down again. And this is called usually benign overfitting. So it's a phenomenon in machine learning, and actually it's explained by the very strong results that we have now with LLM and this type of approaches, that having billions of parameter can still be very powerful in terms of prediction. But today I will just focus on this part of the plot. So the part where you see that as you increase your model with the number of variables, usually your prediction error out of sample goes up. So because of this variance trade-off. Usually in this somehow in this setting, people just want to pick one model. So imagine that you run your linear regression on your favorite package with a given method, and you have your model selection criterion, let's say the lasso or whatever you want to think about. Usually these type of methods in your R package, or if you use Python, whatever, you will usually they give you, so the output will be just one model. So basically you just have a set of variables. This is a good, a reasonable and practical approach, but what we will going to challenge today is exactly this type of approach that gives you only one unique model. Of course, so as I've written here in the slides, if you just give back to the user a single model, of course, it's a very simple message. This is the best model. But are you sure? Are you so confident that this unique model is really explaining your phenomenon well? This is a very hard question to answer. Of course, then imagine that other people, other scientists are studying the same phenomenon as your group is studying, but they don't have the same variable that you have. So they didn't record some variables. And this is common, for example, in genomics. This is common, for example, in genomics. So the idea is that we cannot assume that variables used by one model are important to every well-performing model. So there might be some other things that come into play, and we will see this after as well. There might be some latent structure in your problem, and so these will not be captured by a unique model, so a unique set of variables, but potentially you need to study more than one set of variables. And this is actually what we are going to do, what we've done in this project with this algorithm for sparse model sets. This is what are the issues when you just select one model, is that many different uh, research groups in the world, maybe they're studying the same phenomenon, but they have access to different variables. So you can basically choose in this somehow lottery, uh, especially this related probably about nutrition. So you could say this type of, for example, red wine can cause whatever in this type of cohort of people. This means that maybe other people were studying a similar type of phenomenon, but they have different variables. So they're saying, oh, we found the best model. This is our best model. This explains the phenomenon. But actually, what we would like to do is to have this very big collection of potentially explanatory variables and say something about this whole group rather than just giving one model. So I hope I convinced you at least of why this could be interesting, but we can also think about how theoretically somehow frame this problem. And the theoretical framework comes from a very famous paper of Leo Breiman in statistical science, statistical modeling, the two cultures. If you've never seen this paper, I suggest you to read this. There has been also a recent new one because unfortunately Leo Breiman died. Leo Breiman, if you don't know, is the inventor of random forests. So it's a very an incredible statistician, I would say, and also active in machine learning and in prediction, not only in estimation and inference, as are the usual tasks of statisticians. So why he called this an effect of the interesting of the multiplicity somehow of good models? Why he called this the Rashomon effect? This comes from this Akira Kurosawa movie, where basically, as you can see, there are four people which basically witness an incident, so, an event in which one person dies, and yeah, there are other things that happens into this movie. But the idea is that these people, these four different people, report to the jury. Um, they should actually speak about the same event, the same facts, but the stories are very, very different. They are very different, but they are all very explicative somehow of the event. So somehow, what Leo Breiman was suggesting in his article is that there are a multiplicity of good models, and this is also my experience in practice. So when you go out from the standard packages, either in R, Python, whatever software you use, to just get the best model, and you start to look around at possible other collection of variables, and to look at, for example, what is their prediction error or other form of error metric, you would see that there are many of them not far from the best model. And so these are giving alternative explanations, potentially very different explanation to the phenomenon you're studying. So this is quite important. It should be we should take care and consider also this aspect of the Rashomon the Rashomon effect. Of course, Leo Breiman, as always, was way ahead somehow of his time, and only recently somehow I would say that the literature is catching up on this type of topics. And I would say that the most interesting framework, up to my knowledge, of course, I'm happy if somebody has other type of framework, I would be interested to know also that. But for me, the framework that I found more compelling is the one of Cynthia Rudin and her group, which talks about Rashomon sets, with the famous article JMLR 2019 about all models are wrong, but many are useful. And then they studied variable importance, considering a class of models. The paradigm that she kind of introduces is the paradigm of Rashomon sets. It's a very simple concept. So imagine that you have a model class, let's say linear regression, logistic regression, random forest, neural networks, whatever class you want. You need to pick a loss function, like, for example, the counting error, so the prediction error, or Hamming distance, and an epsilon. And then we can define a Rashomon set to be all the models that are at distance epsilon from a model M star, which is a reference model chosen by you, by the user, for example. Why this is interesting? Because the reference model can be something, for example, that is well established in the literature, and you can check how well with respect to that loss you're doing with your setup model, but also the reference can be the best black box algorithm. Often this is what is used. So imagine that you have your best AI model to predict a phenomenon. And imagine that you're using the prediction accuracy, like the misclassification error, for example, for a classification problem. Then the Rashomon set tells you, let's try to get all the model in a given class of choice. You can choose, for example, a simpler class, or maybe like neural network with less number of layers. And let's see how far they are from the prediction of this best model, reference model. And of course, how far is determined by the epsilon somehow parameter that you need to choose. For example, you could say that if we have, let's say that we have any type of prediction problem where we know that the out of sample accuracy of a neural network, let's say, is 99%. What if, like, I can give you a logistic regression model for the same classification task that has 95 predictions, so it loses just 4% of accuracy? Would you consider this logistic regression model a good model? Also, maybe I can give you more than just one model. I can give you plenty of them. So this type of question can be asked under the framework of Erasmus, and I think it's quite interesting. And now the research is getting, the body of research is growing. So there's been interest both in machine learning and statistics. You can see here some publications for different class of models, and if you're interested, we can discuss more in the Q&A part of the talk. Here is just a representation
Can I can I
of,
ask one question now?
of the help intuition. So as you can see, we have a reference model M star. Then we have the loss function on the y-axis, and of course, all the models that are in this area determined by the horizontal line of the loss of M star plus epsilon, and then the value that I would say of the loss. All these models that are in this region are considered interesting model to and are part of the Rashomon set. But the concept, I think, is just to give you a more graphical intuition about which space where this set of models live in a space. And now I'm going finally to what we propose somehow. We propose actually, yeah, the name is interesting. The SWAG, it stands for Sparse Wrapper Algorithm. The idea is that somehow I told you before that the Rashomon set has this, apart from the selection of a loss of a class of models, the key elements of a Rashomon set are the reference model M star and epsilon. And maybe you can tell me, how can I choose these two things in practice? So maybe they're very hard. This is actually the question that we had as well. So we said, can we come up with something more greedy and more related to the user problems like scientists? And for example, we use this with a lot of doctors. So where maybe they do not have a reference model and they do not have a clear idea of what epsilon will be. So we kind of learn this also with the data. And this is what the sparse wrapper algorithm does. The idea is very simple. So we start, so the idea is that we want also not only to have models of any size, we would like to select model of small size ideally, because the simpler the model it is, the better it is if it can predict well. So the idea of this Rashomon set that we want to exploit is the following. Imagine that we want to build a Rashomon set. What we thought is that if we can have a very sparse model, where sparse meaning that we have a lot of models with a very limited number of variables that can predict as well as a big model, for example, then why we should look at the big model? So these other models are sparser, are easier to interpret. So why we should go, for example, to a black box mechanism? And this was kind of the idea that motivated this, the construction of this algorithm. This is a greedy type of approach. And the idea is that we start by training all the models with just one variable, and we just increase with a parameter which is called Pmax, which detects the maximum model size we aim to select. We will just increase the size of our model up to Pmax in order to determine this set of best models. You can think about our algorithm as a way to estimate a sparse counterpart of the Rashomon set. Um, what are the meta parameters of this algorithm? I told you about Pmax, so we select the maximum model size, and this can be chosen somehow by the user, or for example, for human being, I would say that more already than 10 variables, it's very hard to understand and to picture in mind what's going on. So for example, we could set Pmax. So we just want to check which are the best model that we can get of size 10, for example, with only 10 variables. M is the number of models that we evaluate at each step as we increase the model size. And alpha, of course, is a quantile, which can be somehow the counterpart of the epsilon in the Rashomon somehow framework, which basically tells you a quantile of the loss function that we want to minimize. So somehow, if alpha is 0.05%, it means that at each step we select only the 5% of the best performing model. Of course, our algorithm is built for high-dimensional problems, so not for problems when you can do all possible combinations of variables, because if not, you should do that. You should do what is called the L0 problem, so finding the best subset of variables for the prediction of your given phenomenon. But Swag, of course, does a screening. So the first step, so when we just select model with one variable, can be thought of as a screening step, which has a long tradition in statistics. And if you want, we can discuss more in the Q&A part. Here I have also another representation of the swag set, of the swag procedure. So as I told you, it's very simple. So imagine that let's choose, just for simplicity, a model class. So M stays for a model class. Let's say logistic regression. What you will do with your data set, you will just train one logistic regression with just one variable for each of your variables. So you have P variables. So you can have, given your basically error metric, so the loss function, an evaluation of the loss for each of these models. So you will have P evaluations of the loss at the first step. And you will order them. For example, there would be one variable which is maybe very important and can already have, for example, a prediction error, let's say, of 5%. So like only in 5% of the case it makes mistakes, while other variables can have 10%, 50%, so more than chance level, etc. So here we'll just select a percentage of this model just created with one variable, and then we will combine this subset of variables with models of size 2, and we'll go again to train our class of models, so our logistic regression now with two variables, because we are at point number 2, and then reorder them again with respect to the loss, and selecting which ones are below this given performance quantile alpha, as we said before, this hyperparameter, and we keep on till we reach the Pmax, so the maximum variable size we want to achieve. And then this will give us a set of models. So that's the cool part somehow of the method. You will not get a minimizer, you will not get the best model, but you will get a set of models, all which have a limited number of variables, and they are performing well with respect to the error metric or the loss function you have chosen. So this D function. What is somehow now, maybe this could be a good question at this point. So like, what is the difference between the Rashomon set approach and the swag set? As I told you, in the Rashomon set, somehow you need to give a reference model and you need to give this equivalence range epsilon. In our case, somehow these things are chosen somehow also by the data, in the sense that you can look at your results. So you run the swag, you will have a set of models. You can choose, for example, among them one reference model, for example, and then choose all the others which are at the given distance epsilon. So you can refine the swag to get the Rashomon set. But the idea is that for us, somehow, it's something more related to the data rather than something that you select in advance. You can look at the data, you can see your model, and the alpha, so the performance percentile, and as well the reference can be decided given somehow on your problem, on your specific problem, and somehow you do not need really to have prior knowledge. But of course, there are a lot of point in contact, and how we think about the swag, this is what we call, is somehow a sparser version of the Rashomon set. And so this is actually what you have here in this nice representation. So somehow uh, uh, the Rashomon set, we are selecting a subset with the swag of the Rashomon set, the subset of models which are sparse, so with a limited number of variables, but they are still, for example, at distance epsilon, or in our case, usually is determined by the alpha, by the quantile alpha, a distant alpha from, for example, your reference, whatever your reference model is. So that's the idea. So we are kind of targeting a subset. Why we are targeting this subset of models with small number of variables? Because we believe that this is more informative, in the sense that we have less complexity. As you remember, I don't know if you remember, we started talking about the bias variance trade-off. If I have a limited number of variables in my model, then I will have probably some bias, but the variance will be small. And it's also good for scientists, for practitioners, because they can interpret well the model and not only rely on predictions in a black box way, but really if you have just a model with 5 variables or a collection of models with 5 variables, then of course it's easier to interpret for a practitioner and to understand really what's going on, rather than having billions of variables, or like in a or parameters in some sense. Okay, so here, yeah, maybe just before this slide, there is, of course, a trade-off. The additional cost of working with a set of models is that you increase. So it's true that the model per se, so each element of the set, is easy to interpret, but the issue is that it's hard to interpret the set sometimes. So you may think like, okay, now you told me that it's interesting to have a set of models, but how can I make sense of them? How can I extract information from this set of models? And this is actually, I would say, also one of the main ideas behind also this paper. So not only come up with an algorithm, there may be many ways to create a set of models, maybe even better than what we propose, but I think the idea is really to how to look at this set of models, and we say that to look at the performance of this set of models and how can we interpret them and have understanding of the underlying phenomena is to use a network, so a network representation. And this is a network that we derived for a breast cancer study, which was actually our first application of this algorithm. I'll take some time now a bit to explain what we are seeing here. So each node in the network, each node is mRNA, which is related to breast cancer. When you see the node in green, it means that it has a positive effect. So it protects the woman for breast cancer. So the presence of this mRNA is protective. While if it is in kind of pink, this is negative. So it actually, you will have higher chance to have breast cancer if you have the expression of this mRNA. Why do you see this network? Because you see this network because this network is a representation of a swag set of models. So we basically just run the classical class of models used in medical studies, which is logistic regression on this breast cancer dataset. We get a set of models and we represented the relationship between these models, between the variables in the model, with this network. And when you see an edge between two nodes, like for example, between 21 and 139 3p mRNAs to be thick, it means that these two type of variables are present many times together in this very predictive class of models. So it's interesting to study all these connections between variables. And as the magnitude somehow of the node gets bigger, like here you see 21 is big, it means that variable 21 is very important because it is present, let's say you can look at here, around almost in 100% in all models of the swag set. So you can still somehow extract variable importance with this approach, and in a very graphical and I would say very direct way, especially for a practitioner who can use this method for understanding this phenomenon. And what is the cool thing is that now, if you think about our group of researchers somehow that is analyzing this breast cancer dataset to not be the unique group of researcher which is studying breast cancer, you can see why this type of plots and this type of objects are of immense interest somehow. Because imagine that now another group want to study again breast cancer with another dataset. Rather than having them, as currently still is done, unfortunately, people telling that there is this model that is very predictive for breast cancer, and they tell you 5 or 6 or whatever number of mRNA it has, we gave you an object which contains actually all somehow the possible mRNA and tells you how they are important. And so this is a type of knowledge that can be updated, confirmed, or disproved by subsequent studies. So other people now will not get just a collection of variables, but all of them somehow. And we see which one are more important in one studies, which one in another one, and we can have now a lot of information. Or this is also another thing which is quite cool and it's common in medical studies. Usually, different group of researchers have different machines, for example, especially in genetics. So, for example, they may not be able to capture all the same variables. But with this approach, somehow you can kind of also build unseen model in the data set by just connecting nodes which are important in previous studies. And for example, imagine that in your study, 139 3p unfortunately is not present, but you can look at another collection of mRNAs looking at this plot that can potentially give a very good prediction on a breast cancer dataset, even if you miss one of the variable, which is actually this type of possible approach cannot be done if you just give to the practitioner a single model. So studying all the connections between this variable, I think it's quite interesting for these many reasons that I hope I convinced you at least of the interest of having a set of models, and also why it's quite interesting also to represent them as a set, as we have done in this project. These are also something quite interesting also that was specific to the breast cancer study. We found actually this very nice phenomenon that we have seen that actually if a mRNA was behaving in a way, and so basically an mRNA was behaving differently if it was considered in a different group of models. So like if you consider the mRNA alone or in a network with other mRNA, we were getting different type of prediction in the sense that an mRNA could be protective for breast cancer or negative, so increasing the chance of having breast cancer, depending on which other mRNA it was interacting with. So somehow we call this the antagonistic behavior. So somehow this is something that you can only discover if you look at a set of models, not only just one model. So you can see basically The idea here is that there can be a variable that can behave differently depending on which model it is. So somehow you cannot give to one variable a unique label. Just say this variable is protective for breast cancer. It's not really true from what we've observed. Maybe this variable, being in a model with other type of variables, from protective, it can become harmful. So it's something that this you can only see with a set of models. Of course, we've been working on this type of somehow approach for many for 2 or 3 years now. So we have other type of articles, mostly in the medical domain, but of course we are also studying other type of domains in the latest months. So this is something that has found application in very different field, at least, and actually in any case, in any type of field where you are interested in model selection can be applied and give you something more than just the current paradigm, I would say, of best model. So from my time, I see that I'll take just 5 more minutes to give you basically what are the latest type of work we are doing on this type of project. So I'm already very happy that I was able to talk to you about the general idea about the SWAG and this idea of why it's good to select a set of models and how they can be represented in a meaningful way. But now the question that comes after all these slides probably would be like, how can I know, and this is more related to my statistical interest, how can we do inference on a Rashomon set? Inference means, actually, inference is asking a very, very, I would say, deep question. So it's telling you, okay, SWAG will inevitably select a set of models. So if you run SWAG, there is an R package that you can find online to run SWAG. It will always give you, no matter what, a set of models. But how can I know that these models are meaningful and it's not just random noise? And this means that you need to somehow perform a statistical test, so you go to an inference type of task. So this is actually what we're working on right now. So this is really like a new work that we are doing. So ideally, we would like to do an hypothesis test. Like imagine here I'm doing the case of, let's say, logistic regression or of linear regression, like the counterpart of an F test. So that in linear regression, for example, you have the beta parameters, and the counterpart of saying, am I not picking stuff at random, is meaning that you put the beta coefficient equal to 0. So in reality, so in nature, so in real life, these are not important. There is nothing important in these models. The true beta are equal to 0, but actually SWAG will still output a set of models, and I want to have evidence that actually there are at least one beta that is different from 0. So it's like a classical F test, if you are familiar with linear regression and the F test, the overall F test. Actually, this would be something that I would like to do for the set of models, but this suffers for a lot of multiple testing problems, spurious correlation. It's very hard to show something somehow in this direction. So the idea is that why don't we use the network representation? So the idea is that, is there a difference between a network of variables which is generated by pure random noise and a network of variables which is meaningful? As you can see, H0 you can think is a set given by the SWAG where there is noise. As you can see, there is a lot of connections between the nodes, while the connections are more sparse and there is just a set of nodes which is well connected. And actually, in this simulation study, only variable 1, 2, 3, and 4 were important. As you can see, there is a difference in the pattern of connectivity in the network, and we want to exploit this. And so we want to create a test on this network statistic so that a practitioner can not only run SWAG, but also then do a test to check if the network of model delivered by the SWAG is meaningful or not. So we want to reject H0, so saying that there is not information in your dataset, in order to rejecting H0, somehow accepting H1, saying that there is information, and so you can go on analyzing the swag set. How can we do that? The first approach that usually we do with a problem which is as complicated as this one, because we are doing a lot of steps, so it's very hard to get the null distribution of this test. So we have chosen a specific network statistic, and what we ran was what we're currently working on is to perform a permutation test for the network statistic of interest. How do we choose the network statistic? Actually, it turns out from some experiment that eigenvector centrality is, so the importance of a node in a network is a very important network statistic for the swag network. And so we have used that, and we have run this type of test. And this is a very small simulation study. We don't have to go into much details, but let's say that I want maybe to close saying that this type of test, you can get a p-value with the permutation test. We use as a network statistic the entropy of so the variability of the information of the eigenvector centrality of each node in the swag network, and we have promising first results that tells you that we have good type 1 error control with this permutation test, and the power of the test is increasing as the signal increases. So this is quite good for what we want to do in the future. This is a very fast overview on what we are doing right now. So we are not only working on the estimation, but on the inference on this set of models to tell to the user if this set of models somehow makes sense or if it's just made of noise, and so you should discard it. So you don't have much information with your set of variables. Now we are also into new application in epigenetics, in ergonomics, and we are also interested in latent variables, which is a very interesting topics that we are going to cover as well in the next months. And also other direction are calibrated prediction and other direction in inference, etc. This is the code of the original paper that you can find on arXiv, and here are the main reference. So I think I arrived to 40 minutes more or less. So I'm happy to stop here. Thank you very much for your attention. I hope to have not annoyed you that much, and I'm looking forward if you have some question, doubts, and I have also other slides if you're interested in some particular aspect of the talk. So thank you for understanding.
Thank you very much, Cesare, for the great presentation. So I have a good amount of questions. So maybe I'll start with a few ones. In the definition of your Rashomon set, right? There is this M star, which depends on the user, right? So depends on. Can you hear me? Can you hear me? Hello? We cannot hear you, but probably you're muted right now.
Sorry, can you hear me now?
Yes.
Yeah, but I cannot hear you back. I think the issue is that I was before with my headphones that now lost battery. So I need to understand how to. Sorry. Let's see if you can. See. Maybe can I try to exit and re-enter? Maybe that's the issue. Yeah, I'll come back in a second. Can you speak and try to see if it
Yes,
works?
can you hear me?
Yeah.
Can you hear me?
Hmm. I don't know why. It's
Hello?
first time that happens.
We can hear you though.
It's super weird. Yeah, I know you can hear me, but I cannot hear you. So that's why I think something has happened with the audio. Yeah, you can submit a question to the chat. Yeah. But it's unfortunate that we can't. Okay, maybe I found something now.
Hello?
Okay.
Hello? Can you hear me?
Yeah, so I see the question. I'm sorry, I still cannot. I don't know what happened with my audio.
That's
So
okay.
I really cannot understand what is going on. I cannot even. Yeah, so I'm really sorry about that. Uh, Here, maybe this one, Intel art, whatever. So maybe I can do that. Let's see. Okay, so now it should be okay because I should.
Hello?
Can you talk a bit,
Can
Alessandro,
you hear
maybe?
me? Can you hear me?
Yeah, no. Let's see if now works better.
Hello?
Yeah, I don't know. I'm sorry. Yeah, so I will just look at the yes. So the questions. Thank you. I'm sorry. I'm really sorry about that. But okay, so we'll add mine in order. So I see what is the dependence on M star. Uh, the dependence on M star in the Rashomon set. Yeah. So basically, like when you this in the context of a Rashomon set, you M star is a sort of a reference model. So you can be, um, for example, the best type of model known in the literature. For example, you could think about as a reference model that is known in the literature to perform well, and imagine that now somehow you want to challenge this type of dominance or whatever of this type of model, and you would like to select all models that are not so distant in terms of some metric, which could be prediction, error, or whatever, from this reference model. So somehow, like the Rashomon set um, and enables you to do that. Actually, I think what I can do, I will do something a bit weird now. I can try to join also with my cell phone. Ah, no, but I cannot with that. I need the app. Okay, whatever, I can. I'm sorry. Okay, so yeah, I see another question. Let's see. Um, yeah, exactly. So it's a very good question. So if you have um, the Swag set of model, Swag can also has the advantage of having a unique solution. Yeah, somehow like you can also, um, uh, for example, you can use this approach, which is usually called ensemble learning, to kind of put all these models together to get a unique prediction. Um, I think that the network visualization, yeah, it helps yeah, so it helps you somehow to understand better the also to improve the feasibility of a result. Yeah, so the idea is that imagine that there are different groups of researcher that are working on the same phenomenon. If you just publish, for example, the network and this sort of plots of the variable importance in your study, then other researcher can somehow build on this because they could say, oh, in my case, with my data set, this type of connection between these two variables is more present. Why? Why it is the case? Well, if you just give one model, then all these informations are lost. So people work a lot on a paper, and then they just give you one set of variables which is important, but actually we like to see all these other information on your data set that get completely lost. So for sure it gives you way more than just a prediction, and also since you don't have many variables usually in these models, you can still kind of get a human type of understanding, and you don't have billions of variables. Yeah. Yeah, the parallel with Leo Bremen is I think this is where he got the idea. So he was thinking about random forest, decision trees, yeah, and this type of methods. Yeah, I'm really sorry that would like to hear you, but I don't know what's going on with my computer. Yeah, unfortunately. Let's see, I just try last one. Yeah, let's see if I can just. Yeah, no, I really can't hear. I don't know why. Yeah, sorry. Do you have other? Yeah, sorry, and now it should be there. Should give an indication the variables that have flipping code. Yeah, yeah, exactly. Yeah, so this was actually one of the main results that we get. Actually, I think that is why we um, uh, this paper that we got on the breast cancer was quite interesting. Is really that um, what can happen is that when you just give one models, you may somehow not really understand the direction, the importance of one variable. As you said, like there may be variables that have flipping coefficients. So like maybe this is we have seen this in breast cancer, but I think that this could be the case also in other type of problems. Maybe more of interest to you in your domain. So that you can have one variable that can have this. We call it antagonistic effect. So like in the sense that uh, when it is in combination with other variables, it behaves in a way, and when it is in combination with other variables, it behaves differently. And this, I think, also common in humans, like in our experience. Like maybe when we are with a group of colleagues, we behave in a given way, but when we are with family, we behave in another way. We are still the same person, but we have these patterns which is related more to the higher order connections rather than the variable itself. And so, if you have a network, you can check that. So you can check really what's going on, and you can be more precise. So I think this is another very interesting direction to pursue. And this type of methods, I'm not somehow, as always, I don't want to sell my methods. I just want to underline uh, the problem that we are throwing away a lot of very important information if we just focus on the best model while trying to represent all the connections between these variables with them with a set in a set and with them this higher order connection between them, so edges or maybe hypergraphs, whatever you can think of. It will be very useful to check all this relationship between variables that may be not as simple as we think, like a variable which is always protective for an illness. Maybe it's not the case. So like maybe it could not be the case. Yeah.
Okay, awesome. So thank you very much for your presentation, for the questions. Well, I'm sorry we couldn't interact in the Q&A with
Yes.
things.
Yeah, exactly. So this is a very good point. So um, when you focus on prediction, you can come up with whatever. Like you could say, like your prediction algorithm could be, my friend told me about it. But if it is okay 99% of the time, then it's a good prediction algorithm somehow. So you can come up with any type, with any type of result, and yeah, and while if the focus, as you said, is if the focus is also on explanation, it's more robust. Yeah.
Okay, so thank you very
Yeah.
much,
Thank you.
Cesare.
Thank you.
Yeah, thank you very
Thank you,
much, Cesare, for
Alessandro.
the
I'm
great.
sorry for the audio, but I hope at least I could answer
No
to your
problem.
question.
No problem.
And
Yeah,
thanks a
so
lot
thank you.
for being present and for inviting me. Yeah.
Yes, thank you. Thank you very much. So I'll close the seminar now, but it was great to have Cesare here. Thank you very much for the great presentation, a great conversation.
Bye. Thank you.